Next, we are going to discuss about the properties of waves. These are the 5 major properties of waves. Some of the terms you might have already heard. Reflection, refraction, diffraction. This must be new to you. Diffraction, these two are there in small classes. Polarization, this is also new to you probably, and superposition, this is also probably new to you. So these are the 5 major properties of waves. Reflection happens, and I'll just we are going to discuss about each and everything really quickly, but I'll just give you a brief introduction about each. Reflection happens when a wave reaches a particular boundary. You have learned in small classes, incident ray, reflected ray. So when a wave actually reaches a particular boundary, it will undergo reflection. Refraction happens when a wave travels from one medium to another medium. Then refraction happens because of the change in speed of the wave. And diffraction happens when a wave goes through a small opening. Okay, then something called diffraction will happen. Polarization is completely a new concept. We'll discuss about that. And superposition also, it's like overlapping of two waves. When two waves overlap, the phenomenon we come across. So under reflection, we have to learn 2 types of reflections. One is called the rigid reflection, and the other one is called the smooth reflection actually. All right. And refraction, of course, there are no patterns. Refraction, diffraction, polarization, there are no patterns. We are going to learn about those. And under superposition, due to superposition, there will be 3 phenomena. There will be 3 phenomena. These are the 3 phenomena we'll be coming across due to superposition. They are interference, beats, and standing waves. We already discussed about standing waves. We have a problem whether we can call them waves or not. See, it's a special case. We'll discuss about these things. This is what we are going to discuss under these categories. And first and foremost thing you have to understand is this. All these properties are common for all the waves except for polarization. Okay, I hope you understood that. Reflection, refraction, diffraction, superposition, and all these things, interference, beats, standing waves, all these 4 except for the 4th one, I'll put a star here because it's special, all are common for all the other waves. Polarization happens only in transverse waves. Okay, polarization happens only in transverse waves, not in longitudinal waves. Out of these 5, this is the exceptional case. So when I say about light, can light undergo polarization? Yes. Reason, light is transverse. But can sound undergo polarization? If there's a question like that, no, sound will not undergo polarization because sound is longitudinal. Okay, don't worry about it. We will be discussing about each of these things separately. First, let's start with reflection. Like I said earlier, reflection has 2 types. One is called the rigid reflection. The other one is called the smooth reflection. Now, what is this rigid? These 2 adjectives are all about, rigid and smooth. Let's see. Imagine a wave pulse. Okay, a pulse. I have taken only a pulse. I have not taken the entire wave. Imagine this wave pulse traveling towards a boundary like this. You can see it is a rigid boundary. This is a string, and we have created a pulse on the string, and the string is fixed to this boundary. So we call it a rigid boundary. Let's see what happens when this approaches this point. Now the pulse has reached the boundary, and after it reaches the boundary, now it's going to reflect. Now let's say the time at which the pulse arrived at this point is t equal to 0. And full time taken for the reflection to happen, I'll take it as t equal to capital T. Let's see what happens. So once it is completely reflected, its phase will change like this, completely upside down, because it is a rigid boundary. So when t is equal to capital T is the time taken for this whole process to happen. It will approach the boundary, and then it will reflect the boundary like this. Because it's rigid, the phase will change. Now, what will happen in during the halfway point? This is when t is equal to capital T by 2. When I say capital T by 2, you should understand we are talking about the halfway point. Correct? So at halfway, what's going to happen? Now, this is becoming this. So in the middle halfway, it should be exactly this. Because now we always learned now these particles, the particles at this point, what have they done? Here they have gone like this up, and now they have come down like this, these particles. I hope you understand. That means when they were reflecting halfway, they should have been exactly at the center like this. Correct? So this is what happens during a rigid reflection. Nothing much to worry. they will give you the diagram like this. If the boundary looks rigid like this is what you have to do. The phase will change. Crest became trough. So if a trough came, it will become a crest. Next, we are going to discuss about a smooth reflection of a wave pulse. Imagine a situation like this. There's a wave pulse approaching a boundary like this. There is a bar like thing, and there is a ring which is this bar is frictionless. This ring is free to move up and down. So this kind of boundary, we call it a smooth boundary. Okay, rigid boundary, smooth boundary. From the diagram, you will be able to understand it. So that just like this wave pulse will approach the boundary, and I have taken the time as 0 when it reaches the boundary. And unlike this one, now here what happened was it turned upside down because it's a rigid boundary. But here, since it's a smooth boundary, it will reflect in the same phase. Here the phase will change, here the phase will remain the same. So this is what happens when the reflection is completed. All right. So let's compare this part. What will happen halfway? Right now, the amplitudes have not changed. Actually, I mean the phase has not changed. So during halfway, this is what will happen. Well, this is what happens during the halfway point, because the phase is not changing. So the ring will go up and then it will come back down. If the ring goes down, that means it will give us an indication like this. Since the phase is same, the ring will go up instead of flattening out like this. So this is what you call the smooth reflection. It is a very easy concept. You just have to know this qualitatively. Just identify what boundary they have given, and based on that you decide what kind of reflection is going to take place. Now these pulses I drew were just symmetric pulses. Now even though it doesn't look symmetric, it should be actually symmetric. When you draw it symmetrically. Let's see what's going to happen if this pulse was not symmetric. Now imagine a situation like this. So in this case you can see the pulse is approaching a rigid boundary. So a rigid reflection is going to take place, but this is not symmetric. There's a shorter part and there's a longer part. The shorter part reaches the boundary first. So the shorter part will reflect from the boundary first as well. And we know since this is a rigid reflection, the phase will change. See if you can understand this. Two things have happened. One, this has turned upside down, rigid boundary, so rigid reflection, and whoever came first, the shorter part will go first. I hope you understood that, right? So this is first example. Another similar asymmetric pulse approaches a smooth boundary. So when there's a smooth boundary, we know a smooth reflection is going to take place. So the phase will not change, but whoever came first should be reflected first. Hence, this is how the reflection is going to take place. I hope you understood that. So this is how you identify when asymmetric wave pulses approach a particular boundary. This was rigid, this was smooth. And under this, there is another case where two strings are connected, two different strings are connected, and what will happen during that instance? Imagine a situation like this. This is a light string, that means it's less heavy, light string, and this is a heavy string. So we will learn about this little later, the quantity we are going to use. We decide whether a string is light or heavy based on mass per unit length. Mass per unit length. I hope you understood that. So if the mass per unit length is less, that is considered to be a light string. If the mass per unit length is high, that is considered to be a heavy string. Now you can see when the wave pulse is traveling from the light string to heavy string, you can compare that to this, right? This is like a rigid boundary because this is this is heavier, right? So you can consider this part as a rigid boundary. Now what happens during this reflection is, now here the wave can't go this side because this will stop the wave. But here it's not like that. The wave will continue, a part of this wave will continue moving along this, and a part of this wave will be reflected. Now this wave has a certain amount of energy. The amplitude depends on the energy, we know. So this energy is going to be distributed to this as well as this. So the subsequent pulses, wave pulses, we will have a wave pulse here and wave pulse here. The subsequent wave pulses will have smaller amplitudes compared to this amplitude, because this is the total energy and that energy is going to be separated to 2. Now this question was there in A-level 2019 old syllabus paper, 2019 old syllabus 22nd MCQ. Now there is a small issue in that. The correct answer given was a little different than what was expected. So I will give you the correct answer. If there's any change, I will let you know about that. This is what's going to happen. So let's discuss this in general. A part of this energy will be distributed to this will be transferred through this. So however it came, it will be distributed here. And at this point, the reflection is going to happen. Then when you consider reflection, you have to consider this as a rigid boundary and check whether the phase will change or not. The phase is going to change, right? Now these two amplitudes must be definitely smaller than this amplitude, because this is all the energy. Now that energy is separated into these two. Good. Now the issue we have is we have to decide whether this will have the highest amplitude or this will have the highest amplitude. Based on 2019 scheme, they had given this as the answer. That means this one has the highest amplitude. But equation, we don't have an equation or something to figure that out. There's another lesson we will learn about how to find the speed of these waves. So this wave will travel at a speed, this wave will travel at a different speed. Now I will take V1 and V2. We can definitely compare these two speeds. But we don't have an equation in advanced level to compare these amplitudes. Once if I find out something solid about that, I will share with you in the upcoming tutorials. But as far as I can remember, this was the answer they have given in the scheme 2019, the latest paper. This was given in the scheme. All right. So this is one example. Just know the shapes. Let's decide about the amplitudes little later. Let's confirm 100% confirm about the amplitudes little later. And this is one case where light string is connected to a heavy string. The wave pulse initially is propagated through the light string. Let's see what will happen if you change the strings, this heavy and this light. So this is the opposite case, whatever in the brown color. Okay, purple is the upper one. A wave pulse is propagated through the heavy string to the light string. So if you compare this interface, the point where both the strings meet, you can consider that as a smooth boundary like this. Why? This is light, this is heavy. So from heavy to light means definitely this part is going to be a smooth boundary. What's going to happen after this? A part of this wave is going to be propagated through this, just like this, and a part of this wave is going to be reflected back. All right. So based on that, if you consider what's going to happen, we will be getting an answer like this. This is going to happen. Now this wave is propagated, and here the smooth reflection, so the phase will not change, and this amplitude should be definitely smaller than this amplitude. And since this is a heavy string, I think the amplitude here will be slightly greater than this one, but I will clarify this in the upcoming tutorials once I find a solid source about this concept. All right, just for the time being, try to remember the shapes. Let's discuss about these amplitudes in depth, but at least try to remember the shape. Here you have to think it like rigid reflection. See, the phase has changed. Here it will just propagate. Here it will, however it came, it will propagate, and here smooth reflection, so the phase will not change on the left hand side. So this reflection is this is about reflection in strings. Reflection in strings when the wave pulse traveling along a string meets a boundary. The second properties of waves is refraction of waves. Okay. Now let's see, first of all, let's see why does refraction take place. Now reflection we did, it takes place because the reflection takes place when a wave meets a boundary. Refraction takes place when a wave travels from one medium to another medium. When a particular wave travels from one medium to another medium, the speed of the wave will change, but remember, very important, frequency will not change. Frequency will depend on the vibrating source. So as long as we don't change the frequency of the vibrating source, the frequency of wave will not change, even if the wave travels from one medium to another. Very important thing you have to remember. So, but since the medium is different, density is different between different media, the speed of the wave will change. When I say density, it differs from the normal density we discuss. Here, when it comes to refraction, we say if the medium is less denser, the wave can travel faster. If the medium is denser, the wave cannot travel faster. Normally, that's how we define refraction. Okay. So when a wave travels from one medium to another, what happens? The speed of wave changes, so refraction takes place. In case if the wave is creating an angle with the interface of two media, I will draw that and explain it to you, then the original path of the wave will also change. This is the definition, and I have highlighted this part. But frequency of the wave remains constant when the wave travels from one medium to another. We learnt V is equal to F lambda, correct? V is equal to F lambda. So if frequency doesn't change, when V changes, lambda should change. Why does V change? Because when you travel from one medium to another, the densities of media changes. Densities of media change, so the speed will change. Now, imagine there is a wave traveling from a less denser medium to a denser medium. So let's say our wave is going to travel from denser medium to less denser medium. All right. So in small classes, we have learned we have learned in light how to draw rays and everything. I'll use the same thing. When a light ray travels from denser medium to less denser medium, from rare medium, what happens? The wave will refract away from the normal. If it comes like this, it will refract away from the normal. We have learned that. Now let's see why it actually happens. Now this happens, correct? This is how we normally draw a ray. We call these lines, this red color line, we call it a ray. Okay, that is a ray. But this is not how a wave looks like. This is a ray, a light ray. So what is a ray? A ray actually is a line, an imaginary line, which represents the path of the wave. Ray that actually represents the path of a wave. Now, if they ask you to draw the wave, what you have to draw is you have to draw lines perpendicular to this line. If you draw lines perpendicular to this line, those lines are called not waves, actually wave fronts. So before I go to wave fronts, before we discuss about wave fronts, let's quickly discuss about what will happen when the medium is denser. We discussed when the medium is denser, denser means it will not allow the wave to travel conveniently, denser medium, so the speed will be less. When the speed is less, based on this equation, we know f is constant. If the speed is less, lambda will be less. So wavelength is less, small wavelength. But here, if the medium is less denser, that means it's the opposite. Speed will be greater, so we will have greater lambda. Okay, so when you draw the waves here, the lambda should be small. Lambda small means the gap between the crests must be small. Here the gap between the crests must be larger. Now imagine this is a water wave. This is this is a part of the ocean, the shore of the ocean. This is one different area of water. This is the other different area of water. This part of water is denser. This part of the water is less denser. So when you see from top, from a satellite or from an aeroplane, from a drone, what will you see? You will see the waves are going like this now. The waves are going like this. You will not see the waves, but you will see the crests as lines. Do you agree with me? Right. So when you draw the lines, we have to draw the crests. When I say crests, the distance between two crests is lambda, right? So since the lambda is small, I have to draw the crests closer to each other. Well, this is how the crests gonna look like. And the crests, when you draw, you have to draw those crests, or these are actually called the wave fronts. From top, when you see, you will see the crests like this, the waves, and these are called the wave fronts. And you can see the wave fronts are always perpendicular to the ray. And here, this is the lambda, a small lambda, because it's a denser medium. I'll take it as lambda 1, small lambda, and this ray is traveling at a this wave is traveling at a speed. Let's take that speed as v1. Okay, v1, because I have taken this angle as theta 1, v1. Right. So yeah, good. And then let's see what's going to happen here. Now the ray has refracted. So when you draw the waves here, what you need to do is you need to draw the refracted ray. You choose another color. When you draw the refracted ray, you have to start from these points and you have to draw perpendicular to that, like this. I will draw one and show you, like this. See, now that line is perpendicular to that, and when you continue drawing, it's going to look like this. And then you will draw from here. Right, this point, connect that point, perpendicular. Look at that line in 8. Yes, that's it. Nice. And then you have to draw lines parallel to that. So this is how the wave is going to travel in the other medium. Likewise, you can continue drawing parallel lines to that. I hope you understood this. So see, the gap is higher, okay, because the wave fronts. What am I drawing? The wave fronts. When I draw the wave fronts must be perpendicular to the ray, okay, and this gap is greater because here the lambda will be higher, so lambda 2, and the speed of these waves will take it as v2. Okay, so this is a solid example for refraction taking place between two different waves. The wave came like this, and then the wave will bend like this and go. That is what's happening here. The wave actually came like this, and the wave will bend and go like this. This phenomenon is what we call refraction, and this takes place because of the change in speed and change in wavelength due to change in densities of different media. Okay, right. Now you can see there is a relationship we can figure out, the angle theta 1, theta 2, speed v1, v2, and wavelengths lambda 1, lambda 2. The relationship between these components is given by this equation, friends. v1 over v2 equals lambda 1 over lambda 2, and that is equal to sine I theta 1 over sine theta 2. This is the relationship between these three components. Okay, but remember, the top part is for the denser medium. The top part is for the denser medium, and the bottom part is for the less denser medium. You will understand this equation much more clearer when we study. You will understand it much clearer when we study light, because in light we normally focus more on refraction. For the time being, with this is the relationship between these components when it comes to refraction under this lesson. In light, let's discuss about this much deeper, then you will get a better understanding, hopefully. So this is the summary of refraction. Sometimes based on this equation also they might ask questions. You should be ready. How did this equation arrive? We'll discuss. You will understand that when we do light. And I'll quickly clarify a little bit more about these wave fronts. Now what are wave fronts? Imagine waves. Some waves are traveling like this, parallel to each other. Okay, water waves. Right, this is one wave, and this is another wave, and this is another wave, like this. We have waves like this. When you see from top, when you connect, what you see is these crests. When you see from top, you will, what you actually see is these crests. So when you connect those crests, you will get a line. Am I correct? You will get a line like this. This line is what you call the wave front. When you see from top, you will see these lines. I hope you understand. What are these lines? These are the lines which connect the crests of waves which are traveling together. So those lines are what I have drawn here. Okay, and these are wave fronts, and these are rays. Ray is the path of the wave, the direction at which it's propagating, and wave front is perpendicular to that. Wave front is the collection of the wave front is actually the line connecting all the crests. The third property of waves is diffraction. This must be relatively new to you, diffraction. Now, diffraction takes place when a wave meets an obstacle or an opening when it propagates, and when that happens, when the wave spreads, the waves will spread, and that phenomenon is what we call diffraction. Okay, this is the actual definition. I know this sounds very unclear, very complex, so let me explain that to you with a small diagram. Now imagine there is a wave. Now wave fronts we discussed in the last lesson also. Imagine something like this, a wave. So I have represented the wave by wave fronts. The wave is traveling towards an obstacle like this. Now this is an obstacle. Now the wave can't go past it. So what will happen to the wave? The wave is going to reflect back. So the green color waves I have drawn are the reflected waves, and there is the incident wave. Now this is not diffraction. This is just reflection. But what's going to happen if this obstacle was small? If there's a small opening in this obstacle, let's see what's going to happen. Now consider a situation like this. Okay, now this is a small obstacle, and when there's a small obstacle like this, now the middle part of the wave can't move forward, but this part of the wave and this part of the wave can move forward, but the middle part of the wave is obstructed. So what happens eventually is the middle part is like vacant. Middle part is vacant in the sense this part of the wave is not going to propagate. So the energy of the wave which is propagating from here and here will spread to this side. So eventually we will observe something like this. Something like this. That means the wave will slowly bend towards the inside like this. Okay. Now this is diffraction because of an obstacle. All right. But this is not there really in your syllabus. I just wanted to explain you. This is also a type of diffraction. Imagine there is a beam of light coming from this side. There is nothing here, no light here. There's a beam of light coming out, and let's say there is this a column here, a column. Okay, a light post or something like that. Even behind the light post, from a certain distance from the light post, you will be able to see the light which was generated from here. This. Okay, so that is one example. This is the diffraction which takes place because of an obstacle. Okay, so obstacle. Now let's say how diffraction takes place because of an opening, which is the important part when it comes to your syllabus. Diffraction have taken place due to an opening. Now imagine a situation like this. Now this wave front, this wave is approaching this obstacle. Obstacle in the sense, this is not an obstacle now, this is a opening, correct? Now what will happen? The wave can travel only through this part. All this part, these waves, the upper part and the bottom part are blocked by this part. Only this part is available. So what happens? The wave which can move through this part will move, and these parts are vacant because these waves are not propagating now. Then what happens? The energy of the waves which are moving from here will spread. So eventually you will see something like this, a phenomenon like this. The waves will spread like this. This is what you actually have in your syllabus. This is what you call diffraction. So with diffraction, unlike refraction, in second property we learned, there are no equations and all in your syllabus, but there are equations. Now you can see there is an angle created here, and this is the size of the slit. Size of the slit is, if you take it as d, and the wavelength lambda, and there's an angle. There's a relationship for those. But in A-level syllabus we don't normally learn that. And one more important thing, for us to observe the diffraction clearly, that's a very important condition. Now we know this length, wavelength, correct? That length is wavelength, and the small gap here, I'll take it as d. If you want to observe diffraction clearly, your lambda should be greater than t. That means the opening must be very small. Then only you will be able to clearly see the diffraction. Here also the size, let's just forget about this. This is also diffraction, this is also diffraction. This is the most important thing. So when this d is smaller, then the angle will be larger. That's what you have to remember. It's very important that you know that. Well, this is that angle I'm talking about. So if you really want to know a relationship between these, I think the relationship, if I can remember right, that is lambda equal d sine theta, but I'm not 100% sure, and this equation is not very important to you. That is the relationship here. That is not, I don't think you will be tested in A level about this equation. The only thing you need to know is, if you want to observe a bigger diffraction clearly, that means this condition is important. The opening of the slit must be very small compared to the wavelength. If the opening is larger compared to the wavelength, you will not be able to observe the diffraction much clearer. I'll represent that with another diagram. Let's consider a situation like this. A wave is approaching a larger opening, right? So let's mark the important lengths. We know this length is the wavelength, lambda, and this length is d, correct? This length is d. I'll just mark it, and you can see d is larger than lambda. So when these waves spread, the spreading won't be very significant. It will be only very less, like this, almost straight lines. You can see, right? Almost straight lines. It will be very, very less. It won't be even noticeable. Very less, like this. It will almost be straight lines. So if you want this spreading to happen more, if you want this angle to be larger, so the opening has to be made very smaller. Okay. Now diffraction, phenomenon of diffraction. For example, in real life, where can you see diffraction? All the waves can undergo diffraction. That's a very important thing, every wave. So normally when we say waves, we normally compare between light and sound. Imagine this is a room, this is a door, small door, it's open, and it's night time, and here there's no light, but here we have turned on a light, so this room will be bright. Yeah, you are even though you are standing here now, light waves are blocked by this wall and this wall, but if you are here, you will still be able to see some light in this region because of the light in this room, not because of the light somewhere here. Let's say it's absolutely dark here, but because when you turn on the light in this room, even though there are two walls like this, still you will be able to see some light here. That is because of diffraction. Okay, and one more example. Imagine that there's a room here, that room is closed like this, there's a small opening. Let's say there are some people talking inside this room, but if you are outside this room, still you will be able to hear what they are speaking. The sound waves are blocked here, the sound waves are blocked, but even if you are here, now see, if you are here, these sound waves are not going to reach you, but due to diffraction, still you will be able to hear these sound waves. So those are some phenomena of diffraction we see in our day-to-day life. The fourth property of waves we are going to learn is polarization. Now, what is polarization? We have already done reflection, refraction, diffraction, and now we have polarization. The definition for polarization would be directing a particular wave only in one single plane. Okay. Now, for example, let's say there's a medium. In that medium, we are creating oscillations in different planes. When I say different planes, this is what it means. Now, this is one plane, this is one plane, this is one plane, this is one plane. Okay, you can see it's slant, right? Okay, if you see like this, right? Different planes, one plane, planes, like different planes like that. Okay, so if a wave is polarized, or if a wave undergoes polarization, it will be directed only in a single plane. That is what polarization means. Now, this is going to be the definition of polarization. Now, to explain polarization, let me use this example. Imagine there is a string, and that string is connected to a wall like this. So that's a string. The string is fixed to a wall. Okay, right. Now, at this point, I create vibrations like this everywhere, in every direction, like this. Okay, okay. Now, like this, I do it everywhere. Then what will happen? There are few possibilities. A wave might try to travel like this. A wave might try to travel like this. Another wave might try traveling like this. Okay, that means what I have drawn is the pink color one is like this, and the green color one is like this. I got it? Different planes. Okay, flat line. Another wave might try to go like this. So different planes. This wave is approaching at different planes because the particles are vibrating in different planes. But so this is non-polarized. Here, no polarization. Right. So how do you polarize them? This is what you do. What you have to do to polarize a wave. To polarize these waves, what we do is we create a small slit like this. Okay. Now you do the same thing here. You vibrate this string in every direction arbitrarily like this. So until this part, the waves can travel like this in all different planes. But after this, you can see the motion of the wave is restricted to only one plane like this, only one plane, because these parts are going to act as barriers. So on the other side, the wave will travel only in one plane. So if the wave is going to pass this, the wave will pass only in this direction. Okay. So here only this wave will proceed, but the other waves will have to stop in the middle. Correct. So if you imagine, this is the first plane I was talking. This is the initial plane, which is parallel to this. There can be waves in other planes, but they can't proceed. I just draw the other waves. This like this, but they can't proceed. They will stop. I will draw another wave in another color. I hope you understood that. Now what I have drawn is one wave is like this, one wave is like this, one wave is like this, different planes, right? But after that, wave will proceed only in one plane. That is what you call polarization. You just have to know polarization and everything qualitatively. There is no equation and all. Just try to know this. So here, polarized, we can call it polarized wave. Okay. If you want me to give an example in chemistry, if you have studied organic, you might have learned something called plane polarized light. If a molecule is an optical isomer or an enantiomer, that isomer can rotate a plane polarized light in clockwise or anti-clockwise direction. I hope you can remember that if you have done chemistry. And another example for polarized light is now sun. The light we get from the sun is non-polarized. It's not polarized. It comes in different directions. That's why when the sun is very bright, it's difficult for us to walk on the road because the glare is too strong. When you wear sunglasses, the light is polarized, so that it's less difficult for us. You can see the road even when you wear the sunglass. You can see the road. What is the meaning of that one? The light is incident on the road and it comes to your eye. So it's coming to your eye. When you remove the sunglass, light is coming at your eye at in different planes like this. So when a light comes like this directly to your eye in this direction, flat, that it will be very difficult for you. It will be very difficult for your eye. But if you can control that plane, and if you can direct the light in a different plane, then it will be convenient to you. That's what happens actually in sunglasses. So that is one example for polarization. Now the most important part, you can see the wave which can be polarized, or the wave, if you want to polarize a wave, if you want to observe polarization really, the particles in the medium must be able to oscillate perpendicular to the direction of propagation of wave. If you take this particular wave, this particular scenario, all the waves are propagating in this direction. See if you can agree with me. Here also like that. The direction of propagation is this, but they are oscillating in different planes. Now, for example, if this is the direction of propagation, if this is the direction of propagation, if particles oscillate like this, that is also perpendicular, no? Perpendicular to them. If the particles oscillating like this, up and down, that is also perpendicular, right? Here, if they oscillate like this, that is also perpendicular, correct? And likewise, if you want to observe polarization, particle must oscillate perpendicular to the direction of propagation of wave. If the particles are oscillating like this, parallel to the direction of propagation of wave, there is no need to be polarized. It's like they are already polarized, correct? Like this, if they are oscillating parallel. So very important thing you have to understand, only the transverse waves can undergo polarization, because in transverse wave the particles are actually oscillating perpendicular to the direction of propagation of wave. But in longitudinal wave, since the particles are oscillating parallel to the direction of propagation of wave, it cannot be polarized, because there is no point of polarizing it. It is just traveling in one single plane. I have written the summary of what we discussed here for your convenience when you make notes. For polarization to take place, particles in a medium should oscillate perpendicular to the direction of propagation of wave. So only transverse wave can be polarized. Longitudinal waves do not undergo polarization. Right. Now when you talk about polarization, let's discuss about two very commonly discussed waves. One is light and one is sound. Okay. So when you talk about light is a transverse wave. I'll put TS, TW actually, transverse wave. Sound is a longitudinal wave. So light can undergo polarization. I'll just put a tick because it can undergo polarization. But sound, since it is a longitudinal wave, it cannot undergo polarization. Okay, I hope you understood that. I hope this is clear. Again, just like diffraction, you just have to know this qualitatively. Apart from that, we don't have any complex equations or anything here. All right, the next property, the fifth property of waves, it's called the superposition of waves. Now, when we discuss about superposition of waves, we will be discussing three more phenomenon which are related to superposition of waves. We discussed that in the introduction part: interference, standing waves, and beats. These are the three we are going to discuss. So first of all, let's see what this superposition is all about. Superposition of wave happens when two waves overlap or when two waves interfere. Okay, so when there is a medium, that medium can be anything, a string, water. In a particular medium at a particular position, two waves can't exist, because when you say a wave, in a particular medium, a wave is created when the particles displace. So, when two waves are in one position, the same particle can't be at two places, correct? The particle has to be at one place. So, when two waves overlap, superposition takes place. To understand about this furthermore, we have something called principle of superposition. Let's see what principle of superposition actually means. Imagine that there are two waves traveling in the same medium and then they meet. Okay, so when the two waves meet, the displacement of the resulting displacement will be the addition of the individual displacement of each wave. So let me explain that with a diagram. Imagine there are two wave pulses actually. This wave pulse is traveling to the right, this wave pulse is traveling to the left, and at one point they will meet each other. This is the situation when they meet. Now, like I told you, this particular particle is where this is the place where they meet. So when they meet, this particular particle can't be at two places. So instead, this particle has to be at one place. So if this amplitude is simple A and if this amplitude is simple B, when they undergo superposition, the resulting amplitude will be the addition of these two because the amplitudes are in the same direction. Well, at this point, this is what will happen. Okay, so this is what you call principle of superpositions. When two waves meet at a certain point, the resulting displacement will be the addition of the displacement of each wave. All right. Now, here the waves are traveling in the same phase. Now, same phase in the sense both are crests, crest and a crest are meeting. So, the displacement is increasing. So, this kind of superposition, we have a special name. We will discuss about that next. Okay. So, the first phenomenon we are going to discuss based on superposition is what we call interference. Now, interference means the overlapping of two waves actually. So, when two waves overlap, there are two types of interference which take place. One is called the constructive interference and the other one is called the destructive interference. Now, when two waves which are in phase, that means crest and crest are meeting, then the amplitude, resulting amplitude is increasing. That's what you call constructive interference. So, let's now we have discussed, I just wanted to explain what this principle of superposition is. Then I'll redraw this here and let's see what happens afterwards when these once these waves overlap. The waves are traveling towards each other and they will meet. When they meet, their amplitude increase. Then eventually they will continue to move the way they approached each other. Right? This is the small one with the small amplitude moving towards the right. This is the one with the larger amplitude, relatively larger amplitude moving towards the left. This is what happens. So this phenomenon is what you call constructive interference. If the interference is constructive, the resulting amplitude will increase. It will be greater than these two interference. All right. So the opposite of this is going to be if this and this are in opposite phase. That means one should be crest and the other one should be trough. When that happens, we instead of constructive, we will have destructive interference. Let's see what that is all about. The wave pulses are traveling towards each other and they are going to meet, and this is what happens when they meet. But the problem is this particle can't be at two places. So we have to consider the principle of superposition. Now, if you take this as simple A and this as simple B, the resulting wave will be A minus B. I said it's the addition, but since it is displacement, it's vector, so we have to consider direction. So the resulting wave is going to look like this. When you consider these two, the resulting wave will be, you have to subtract this part from this part, hence it's going to be somewhat shorter like this. Okay, so you can see this height is going to be how much? It's going to be A minus B, and eventually just like this the waves will continue traveling in their own paths. Okay, again this is A, this is B, they will move apart each other just like this. Okay, they will meet and then they will go away from each other as if nothing happened. That's what happens during constructive and destructive interference. So this is going to be the destructive interference, and during destructive interference the resulting amplitude reduces. Now what's going to happen if two wave pulses of equal amplitude undergo constructive and destructive interference? It's very easy. Now this is A and B. What if this was A and this also was A? What if this was A and this also was A? Right? Let's see. If the amplitudes are equal, then the resulting amplitude will be double. That's very easy. It's a normal math. A plus A, 2A. And if equal amplitudes, wave pulses of equal amplitudes in opposite phase meet each other, that means something like this is going to happen, where the amplitude will be 0. Now this part is a very common question we get, and they will ask you what is the energy of the particle at this point. Alright. Now if you take the particle here, these two particles carry the maximum potential energy, because they have moved maximum distance from their original positions. So there is energy here, between stored in these two particles. But here it looks like there is no energy. It's absolutely flat. But remember, energy cannot disappear just like that. Okay. So what happens here is this particle is actually either moving down or up at its maximum velocity. That is what's happening to this particle. Here this particle and these particles will be at rest, but they have potential energy. So you have to add this potential energy and this potential energy. In this there is potential energy, but in this the potential energy is 0. That means the particle has maximum velocity. That means the kinetic energy is maximum. Only kinetic energy will be there, but the potential energy is 0 in a situation like this. This is a very common question we get during MCQs. Alright, good. So you have to know this is an example for interference. If you want me to define interference in simple ways, the change in resulting amplitude when two wave pulses or waves overlap. And there are two types of interferences. That is, one is constructive interference and the other one is destructive interference. Right. Now for constructive interference, when you consider the phase difference is going to be 0. Reason, both are crests. So for constructive interference to happen, the phase difference has to be 0. Okay, I have marked here phase difference is equal to 0. The reason is the phase difference equal to 0. The reason is two crests are meeting. If two troughs are meeting, that is also fine. That is also in constructive interference. Okay, because the amplitude is going to anyway get added. Correct? Alright, the phase difference for constructive interference is 0 because crest and crest are meeting. Okay, for crest and crest, same phase. But here, a crest and a trough are meeting. So for destructive interference, what is going to be the phase difference? Okay, let's quickly do a recap of what we learned earlier. When you take a wave, this is how the wave looks like, a single wave, right? And when you consider the phase angles, we know the phase angles. This is 0. This is pi by 2, this is pi, and this is 3 pi by 2, and finally this is 2 pi. And we learned, even in the previous classes, we learned that this is a trough, this is a crest actually, this is a trough. The phase difference between those two, it's going to be pi. Correct? So pi means it's 180 pi radians, if not 180 degrees. So for destructive interference to take place, a trough and a crest should overlap. That means the phase difference must be 180. Now, I hope you understood this. Okay. Now, these are the type of questions you get, very simple ones. All these things. And let's move one step ahead, and you get these kind of questions also. Imagine, I'm going to use this space for this question. Imagine there are two point vibrators, small point vibrators, and they are inside water. Point vibrator 1, point vibrator 2, this is water, and we are observing from top, correct? So when you put on this point vibrator, here a vibrator, it will vibrate like this, and water waves will go everywhere like this, correct? Imagine you put a small pebble inside a pond, water waves will go like this. Similarly, you do a small vibration here, so the water waves will travel like this. Two vibrators, each will create circular shaped wave fronts, correct? When you see from top, the ripples formed in the pond, they will look like circles, right? So let's see, let's plot that into a diagram. I have used red color for one point vibrator. This point vibrator will be creating circular wave fronts like this. Okay, we discussed about wave fronts. So if these circles are the wave fronts, and each circle actually represent the crests. I hope you can remember these circles represent the crests. So crest, 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 crest. Hence, the exact middle point between two crests, what will we have? We will have a trough. So there will be another crest here, crest, trough, crest. So the exact middle point will be the trough. So I will use broken lines to mark the troughs, which will be very important for us to analyze this situation. Are we clear? The complete lines are representing the crests and the broken lines are representing the troughs of the first point vibrator, which is in red color. And now I have drawn the other set of wave fronts created by this particular point vibrator. I am using the green color for this. So the complete circles, we know they represent the crests. So exactly between two crests we will have the troughs, just like in this one. Let me draw those. I hope this picture is clear for you. I know it's a mess, but if you know what it really means, you will not get confused. The complete lines in both the circles, in both the diagrams represent the crests, and the broken lines in both the circles represent the troughs. Correct? All right. Now, waves are moving this way, waves are moving this way. So what will happen? Interference will happen. All right. Now they will give you a diagram like this in your paper, in your question paper, and they will ask you to find out the constructive interferences and the destructive interferences. All right, fine. So what is a constructive interference? Constructive interference means two crests meeting, if not two troughs meeting, two wave pulses in same phase should meet. I will mark certain points, see if you can agree with me on this. I am using this color. All right, so these points, this point, this point, this point. I'll use a dark circle, this point, and this point. That's enough. If we mark too much, it might be, never mind, I'll mark one few more. See what is happening? I have identified the points where two complete circles are meeting. Both the complete circles are meeting, these points. All right, so I have chosen this mark. So what does this really mean? What does this mean? The complete line of red and complete line of green are meeting. What is the meaning of that? Complete line of red is the crest, complete line of green is the crest. So this is happening. Okay. So when a crest and a crest meet, what will happen? We will get a constructive interference. So these dots are examples for constructive interference. I will put CI, you should understand that is constructive interference. So when you draw this diagram in your note, you can draw a bigger diagram and mark these points. All right. Now let me use a different color, perhaps this color, and I'm going to mark other points. Now let's try to mark the points where the broken lines are meeting. The broken lines. Now this part, I'll draw a circle, maybe circle, 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 circle. Okay, this color, right? And here also same thing is happening. What are these circles I'm drawing? Those are the circles where the broken lines of red and broken line of green are meeting. Okay, so this circle. What is the meaning of this? Broken line of red and broken line of green are meeting. That means trough of this and trough of this are meeting. When you say trough and trough, again they are in same phase. So again it is constructive interference. Okay, so the points we have marked, these points and these points, all of them are examples for constructive interference. Okay, right. Now let's try to identify, obviously, destructive interferences. What is destructive interference? Destructive interference is when crest of this and trough of this should meet. If not, crest of this and trough of this should meet. So I will first start with these points. Let's try to find out crest of this and trough of this. Crest of this is complete line, trough of this is broken line. So look at these points, this one, this one, this one, and this one, this one, this one. The blue color circles I'm using, yeah, this one. I hope you got that, right? So the blue color circle I have used are for crest of red and trough of green. When a crest and a trough meet, we know that is going to be destructive interference. Destructive interference. All right. So I know it's a bit now it's getting a bit complicated, but if you draw a larger diagram and if you mark, you will get everything correctly. Okay. Right. Good. For your convenience, I'll just mark. Later, you can, when you draw, you can be mindful about it. Now, when you say this part, that is a complete line of red and complete line of green are meeting. So this one, broken line of red and broken line of green are meeting. Okay, and if you take this one, destructive interference, in that one, complete line of a red and broken line of green are meeting. So crest and trough. And there's one more example. What is that going to be? That is going to be trough of this and crest of this meeting. That means a broken line of red and complete line of green. I sense this part. I'll just draw a triangle. Okay, broken line of red, complete line of green. You also can mark if you draw a larger diagram like this. So I'll use a rectangle orange color part. Okay, then that will look like this, no? And crest and trough and crest, again opposite face, so destructive interference. All right, now for your convenience to get the proper diagram, this. Okay, so this is how you identify constructive interference and destructive interference when they give you complex wave fronts like this. And here is the diagram if you want to have a closer look. I know when I drew it from far it was not very evident. I have drawn, and let's have a closer look here. So when you have a closer look there, you will be able to see all the points I have marked, the colors I have used. It's not that hard. If you draw the diagrams properly, you will get it right. Okay, right. So have a look at it completely. We have identified four different cases. Complete line of red meeting complete line of green, broken line of red meeting broken line of green, complete line of red meeting broken line of green, broken line of red meeting complete line of green. The first two cases were constructive interference, and the next two cases were destructive interference. This is the summary. I hope you got that. Instead of a wave front, here we were comparing wave fronts. Instead of a wave front, if you want to consider the whole wave and speak about constructive interference and destructive interference, this is how it's going to be. Now, if you want constructive interference to take place, both the waves should overlap or should meet in phase. So, two waves. I'm going to draw two waves like this. One, this wave, and the green wave are going to meet. Okay, now let's add these two waves. When you add these two waves, now what's going to happen? When you add these two waves, you will get a single wave. Crest and crest are meeting, correct? Trough and trough are meeting. That means there's zero phase difference. There is zero phase difference. That means the resulting wave will be looking like this. It will have a larger amplitude like this. Not only with wave pulse, even with waves we can consider. So this is the constructive interference. Okay, right. Similarly, if you want to observe destructive interference with two complete waves, they should meet out of phase. They should meet in opposite phases. That means a crest must be meeting the trough. So here I should be drawing a trough, and a trough must be meeting crest. And remember, these two waves have same amplitude. I have taken like that. Now when you add these two waves, what's going to happen? Okay, both have same amplitude, so crest and trough are meeting, trough and crest are meeting. Finally, the resulting wave will be like this, a flat one. It is destructive interference. I have considered this case. Okay, both the waves have same amplitude. So in terms of waves, if you consider, this is how constructive interference and destructive interference happen. In terms of wave pulses, if you consider just one pulse, that is easy for us to analyze. It's going to happen like this. So this is the summary of interference. In the next tutorial, we are going to discuss about the other two phenomena of superposition of wave, standing waves and beats.